Picture a typical American strip mall on an ordinary Tuesday afternoon in Cincinnati, Ohio. The year is 2005, and inside one of the stores, a model airplane hobby shop, a 69-year-old man named Lee Spievak is demonstrating a remote-controlled airplane to a customer. Lee loves his work. He's been passionate about model airplanes his entire life, and working at this hobby shop lets him share that passion with others every day. He's showing off one of their newest models, a beautiful replica with a propeller that spins at incredible speed when the motor engages. Lee reaches out to adjust something on the airplane while explaining its features to the customer. For just a split second, his attention drifts from where his hand is positioned. His middle finger moves too close to the spinning propeller, and in an instant, the blade catches his fingertip. There's a flash of pain, a spray of blood. Lee pulls his hand back and looks down at his finger. The entire tip is gone. Half an inch of flesh, nail, and bone has been sliced cleanly off. The propeller blade is so sharp and moving so fast that the cut is almost surgical in its precision. Lee and the customer both stare in shock at the severed finger. They search frantically for the missing piece, thinking maybe it can be reattached. But it's gone. Vanished somewhere in the hobby shop, probably flicked away by the spinning propeller into some unreachable corner or crevice. They never find it. Lee wraps his bleeding finger in towels and heads to the emergency room. The doctors examine the wound and deliver the verdict he's already expecting. Without the severed piece to reattach, there's nothing they can do except clean and bandage the wound. The fingertip is lost permanently. It will heal over with scar tissue, leaving him with a shortened, blunted finger for the rest of his life. Lee goes home dejected. He's 69 years old. At this age, you don't bounce back from injuries the way you did when you were young. The body's capacity to heal diminishes decade by decade. And fingertips don't grow back, everyone knows that. Salamanders can regrow limbs, starfish can regrow arms, but humans? No. What's lost is lost forever. Except Lee Spievak has something most people don't have. He has a brother named Alan who works in regenerative medicine. And Alan has been following the research of a scientist at the University of Pittsburgh named Dr. Stephen Badylak. Dr. Badylak has been working with something extraordinary, a powder derived from pig bladders that seems to do the impossible. It seems to trigger tissue regeneration in ways that shouldn't be possible according to conventional medical understanding. When Lee calls his brother to tell him about the accident, Alan immediately thinks of Dr. Badylak's work. He asks Lee to hold off on seeing the hand surgeon for follow-up treatment. Alan has an idea. It's experimental, it's unproven in humans for this specific use, but he thinks it might work. A few days later, a package arrives at Lee's house. Inside is a small vial containing a fine powder that looks, as Lee will later describe it, like Kraft Parmesan cheese. There's a note from Alan with simple instructions. Apply a small amount of the powder to the wound every other day. Keep the wound clean, and wait. Lee Spievak is, by his own admission, not a man who asks a lot of questions. His brother says to try this powder, so he'll try it. He doesn't particularly care at this point what it's made of or where it comes from. His fingertip is gone. The doctors say it won't grow back. What does he have to lose? He sprinkles a bit of the powder on his wounded finger and covers it with a bandage. And then something happens that will make Lee Spievak the center of a media storm 2 years later when his story finally goes public. Something that will have researchers and doctors arguing about what's possible and what's not. Something that will raise questions about the limits of human regeneration and whether we've been underestimating the body's capacity to heal itself. His finger starts to grow back. Part 1. The Science of Regeneration. Rocky the Dog and the Discovery. To understand what happened to Lee Spievak's finger, we need to go back in time. Back to 1985. Back to a veterinary practice and a dog named Rocky. Dr. Stephen Badylak was a veterinarian at the time, working in a small animal practice. Rocky was a German shepherd who had been in a serious accident. He had extensive damage to his abdomen, and conventional treatment wasn't working. Rocky was dying, and Dr. Badylak knew it. In a last-ditch effort to save the dog's life, Dr. Badylak tried something unusual. He used a section of small intestine to patch the damaged area in Rocky's abdomen. Not synthetic material or a graft from another animal, but actual intestinal tissue. The reasoning was simple: intestinal tissue is incredibly resilient and regenerative. The inner lining of your intestines completely replaces itself every few days. It has to, because of all the wear and tear from digestion. So Dr. Badylak thought maybe that regenerative capacity could help repair Rocky's damaged tissues. He performed the surgery, patched the wound with the intestinal material, and sent Rocky home with his owners, expecting that the intestinal graft would simply serve as a temporary patch until Rocky's body could generate scar tissue over the damaged area. But when Rocky came back for a follow-up exam weeks later, something unexpected had happened. The intestinal patch hadn't just acted as a bandage. It had triggered actual regeneration. The damaged tissue had rebuilt itself. Not with scar tissue, but with functional, healthy tissue. Dr. Badylak was stunned. He began researching what exactly in that intestinal material could trigger such profound regeneration. And what he discovered would change the direction of his entire career. The secret was in something called the extracellular matrix. Let me explain what extracellular matrix is, because it's crucial to understanding this entire story. Your body isn't just made of cells. Between and around all your cells is a scaffolding, a three-dimensional network of proteins and other molecules that gives structure to your tissues. This scaffolding is the extracellular matrix, often abbreviated as ECM. It's the glue that holds everything together at the cellular level. The extracellular matrix is made mostly of proteins like collagen, elastin, and fibronectin, along with various sugars and signaling molecules. But it's not just passive structure. The ECM is active. It communicates with cells, tells them what to do, and guides their behavior. When tissues are damaged, the extracellular matrix plays a crucial role in healing. But typically in humans, that healing process results in scar tissue. Scar tissue is functional enough to close a wound and provide structural integrity, but it's not the same as the original tissue. Scar tissue is disorganized. It lacks the fine structure of healthy tissue. It doesn't have full sensation or function. But Dr. Badylak discovered something remarkable about the extracellular matrix from the intestinal submucosa, the layer of tissue that supports the intestinal lining. When this ECM is implanted into a wound, it doesn't lead to scarring. Instead, it triggers regeneration. It somehow tells the body to rebuild the original tissue rather than just patching the wound with scar tissue. Dr. Badylak spent the next several years studying this phenomenon. He experimented with different sources of extracellular matrix. He tried intestines from various animals. He eventually settled on pig bladders as the most practical source. Pigs are abundant. Their genetic makeup is similar enough to humans that their ECM works well in human bodies, and from a regulatory standpoint, the FDA has a long history of approving pig-derived medical products. The process for creating the regenerative powder is surprisingly straightforward, at least in concept. You take a pig bladder and thoroughly clean it to remove all the pig cells. What remains is the pure extracellular matrix, the protein scaffolding stripped of all cellular material and DNA. This ECM can then be processed into various forms, including a fine powder. The key insight is that this powder, when applied to a wound, acts as a signal. It tells the body's stem cells to migrate to the area. It provides a scaffold for new tissue to grow on. And crucially, it prevents the formation of scar tissue by instructing the body to regenerate rather than simply repair. Dr. Badylak tested this approach in numerous animal studies. He used ECM scaffolds to regenerate damaged tendons. He used them to rebuild portions of urinary bladders. He saw Achilles tendons grow back in dogs. He saw complex tissue structures regenerate in ways that shouldn't be possible according to standard medical understanding. The results were so impressive that Dr. Badylak began speaking at medical conferences about his findings. And that's where Lee Spievak enters the story. Lee Spievak was a former Harvard surgeon who had moved into the field of regenerative medicine. He attended one of Dr. Badylak's presentations at an orthopedic surgeons conference in Atlanta. Dr. Badylak showed his data, explained his findings, and essentially said, "Look, we can trigger regeneration in animals using extracellular matrix. This could revolutionize medicine." And according to Lee Spievak, who recounted this story later, most of the attendees seemed skeptical or uninterested. They listened politely but didn't engage much with the ideas, but Alan was fascinated. He approached Dr. Badylak after the presentation. They struck up a conversation that turned into a friendship and an informal working relationship. Alan became convinced that Dr. Badylak was onto something profound. He eventually started a company focused on using extracellular matrix scaffolds to promote healing in injured animals. And then, years later, his brother Lee called with news about the model airplane accident and his severed fingertip. Alan immediately thought of the ECM powder. He knew it had worked in animals. He knew Dr. Badylak had seen remarkable regeneration. Could it work on a human fingertip? There was only one way to find out. So Alan sent his brother a vial of the powder with those simple instructions. Apply it every other day. Keep the wound clean, see what happens. Lee began the treatment, not really expecting much. He was just following his brother's advice, figuring it couldn't hurt to try. The second time he applied the powder, Lee noticed something. The wound looked different. It looked like new tissue was forming. Part 2, 4 weeks of growth. Lee continued applying the powder every other day, exactly as his brother had instructed. And each time he changed the bandage and looked at his finger, he saw remarkable changes. The wound wasn't just closing over, it was building up. New tissue was forming from the base of the wound, pushing upward. Day by day, his finger was getting longer. By the end of the first week, Lee could see definite growth. The stump wasn't a stump anymore. New flesh was filling in where the fingertip had been severed. By the second week, the growth was unmistakable. His wife looked at it and couldn't believe what she was seeing. His brother Alan was thrilled but not entirely surprised. This was what the ECM powder was supposed to do, based on the animal studies. But seeing it actually happen in a human being was still extraordinary. By the third week, Lee's finger was approaching its original length. The tissue was pink and healthy looking. It wasn't scar tissue. It didn't look like the typical healing you see after an amputation. It looked like actual finger tissue regenerating. And by the end of the fourth week, the wound had completely closed. Lee's finger had sealed up. He had a fingertip again. But the regeneration didn't stop there. Over the next few months, more refinements occurred. The nail began to grow back. Skin developed its normal texture. The fingertip took on its proper shape, complete with the natural curves and contours of a normal finger. 4 months after the accident, Lee Spievak's finger looked normal. Completely normal. If you saw his hand, you wouldn't know anything had ever happened to it. But the truly remarkable part, the part that convinced Lee this wasn't just ordinary healing, was the function that returned. Lee had complete feeling in his regenerated fingertip. When someone touched it, he could feel it. When he pressed on something, he could sense the pressure. He had sensation that shouldn't be there. When doctors reattach a severed fingertip surgically, the nerves typically don't regenerate properly. Patients usually have little to no sensation in the reattached portion. They might have some gross motor function, but fine sensation is gone. They can't feel pain or pressure normally. The nerves simply don't reconnect in a functional way. But Lee's finger had full sensation. The nerves had somehow regenerated and reconnected properly. He could feel everything that he could feel before the accident. He also had complete movement. All the tiny muscles and tendons that control finger movement had somehow reformed. He could bend the finger, straighten it, use it to grip objects with his normal strength and dexterity. Even the fingerprint came back. The unique whorls and patterns of Lee's fingerprint regenerated on the new fingertip. This is significant because fingerprints are determined by the precise structure of skin ridges, and for those patterns to regenerate correctly suggests that the tissue regeneration was following some kind of blueprint, either genetic or encoded in the remaining tissue, that told the new cells exactly how to organize themselves. Lee began using his finger normally in his daily life. Working at the hobby shop, handling tools and model airplane parts, typing, writing, everything he could do before the accident, he could do again. And here's a curious detail that Lee noticed. His fingernail on the regenerated tip grew faster than the nails on his other fingers. Not dramatically faster, but noticeably faster. As if the regenerative process had kicked the growth mechanisms into a higher gear, and they hadn't quite returned to normal speed yet. For Lee Spievak, this was simply amazing. He'd expected to live the rest of his life with a shortened, scarred, numb finger stump. Instead, He had a fully functional finger that looked and felt completely normal. But he didn't make a big deal about it at the time. This was 2005, and Lee was a private person living his life. He told some friends and family about what happened, showed them his finger, and marveled at the result. But it wasn't until 2 years later, in 2007, that his story would become public and cause an international sensation. What changed in 2007? Dr. Stephen Badylak's work was gaining more attention in the medical community. His research papers were being published. Other researchers were beginning to explore extracellular matrix applications, and the US military was taking notice. The Army was interested because they had soldiers coming back from Iraq and Afghanistan with severe injuries. Soldiers who had lost fingers to explosions or combat injuries. The military wanted to know if ECM powder could help these soldiers regrow at least partial fingers, even if not the complete digit. Even growing back an inch of tissue could make an enormous difference in functionality for someone who had lost multiple fingers. The Army Institute of Surgical Research in San Antonio began planning clinical trials to test extracellular matrix on injured soldiers. And as part of the background research for these trials, someone mentioned Lee Spievak's case. A reporter from the BBC named Matthew Price got wind of the story and decided to investigate. He traveled to Cincinnati to interview Lee and see the finger for himself. And what started as one BBC report turned into a global media phenomenon. Part 3: The Media Storm and the Skeptics. When the BBC aired Matthew Price's story about Lee Spievak and his regenerated finger in April 2008, it spread like wildfire across international media. Within days, Lee Spievak's face and his finger were on television screens and websites around the world. CBS News picked it up, CNN covered it, newspapers from London to Tokyo ran articles about the man who grew his finger back. The coverage was sensational. Headlines proclaimed medical miracle, regenerative powder works magic, pig bladder powder regrows severed finger. Lee Spievak became an overnight celebrity in the medical and scientific world. The story had all the elements that make for compelling journalism: a shocking injury, a mysterious powder that sounds like something from fantasy, dramatic before and after photos, and most importantly, a seemingly impossible outcome that defied common medical wisdom. The media dubbed the extracellular matrix powder pixie dust, a name that delighted Lee and made the story even more captivating to the public. Here was real-life magic happening in a Cincinnati hobby shop. But along with the excitement came scrutiny. And not everyone was convinced that what happened to Lee Spievak was as miraculous as it appeared. The skeptics started raising questions almost immediately, and their questions were reasonable and worth examining. The first wave of skepticism came from hand surgeons and specialists in finger injuries. They looked at the photographs of Lee's injury and his regenerated finger and said, "Wait a minute, this doesn't look like a case that required regeneration. This looks like a normal fingertip injury that healed naturally." Professor Simon Kay, a hand surgeon at the University of Leeds, was quoted saying it looked like quite an unremarkable healing of an ordinary fingertip injury. He suggested that the injury might not have been as severe as initially described. This is a crucial point, so let me explain the anatomy of fingertip injuries and why the severity matters. Your fingertip has several layers and structures. There's skin, subcutaneous fat, connective tissue, bone, the distal phalanx, and the nail bed. The nail bed is particularly important because it contains stem cells that have the natural capacity to regenerate tissue around them. If a fingertip injury occurs but preserves at least some of the nail bed, the finger has a natural ability to regenerate itself to some degree. Not complete regeneration of bone, necessarily, but significant regrowth of soft tissue. This is actually well documented in medical literature. Children especially can regenerate fingertips remarkably well if the nail bed is intact. The skeptics pointed out that in Lee's before photos, you can see that some nail bed was still present. The injury, while certainly severe and painful, might not have taken off as much of the finger as Lee initially believed. Maybe in the shock and confusion of the accident, the injury appeared worse than it actually was. If even a small portion of the nail bed remained, the skeptics argued, then what Lee experienced might have been natural regeneration that would have occurred anyway, even without the pig bladder powder. The powder might have accelerated or optimized the healing process, but it wasn't creating regeneration where none would have occurred naturally. Professor Stephen Minger from King's College London was even more skeptical. He questioned the nerve regeneration claims. When fingertips are reattached surgically, he noted, nerves don't regenerate properly, and patients don't regain normal sensation. So how could Lee have full sensation in his regrown fingertip? Minger suggested that Lee's description of his injury might have been inaccurate, that perhaps the nerves were never actually severed in the first place. Other critics pointed out potential conflicts of interest. Lee Spievak, Lee's brother who provided the powder, owned a company that was commercializing extracellular matrix products. Dr. Stephen Badylak had patent rights on ECM applications and advised Allen's company. There were financial incentives for everyone involved to present this case in the most dramatic, successful light possible. And then there was the problem of documentation. Lee didn't seek immediate medical imaging or detailed clinical documentation of his injury and subsequent healing. There were no X-rays showing bone loss. No detailed medical records tracking the regeneration process week by week. Just Lee's testimony, some photographs, and the dramatic before and after comparison. For a case being presented as a potential breakthrough in regenerative medicine, the documentation was sparse. And in science, extraordinary claims require extraordinary evidence. Dr. Stephen Novella, a neurologist and science communicator, wrote extensively about the Spievak case on his blog Science-Based Medicine. He didn't dismiss the possibility that extracellular matrix could enhance healing. But he was critical of how the media had run with the story without proper skepticism or fact-checking. Novella pointed out that fingertip regeneration, while impressive, is actually the easiest form of human regeneration. It's at the periphery of the body, where blood supply is good and the structures are relatively simple compared to something like an organ or a limb. Even without intervention, fingertips sometimes regenerate surprisingly well, especially in children and even in some adults if conditions are right. So the question became, did the pixie dust actually cause the regeneration? Or did it simply not interfere with regeneration that would have happened naturally? This is the heart of the scientific controversy. And it's a controversy that persists to this day because we don't have enough data to definitively answer the question. What we do know is this: Lee Spievak's finger healed remarkably well. Whether that healing was accelerated or enhanced by the ECM powder, or whether it would have happened anyway, remains uncertain. But regardless of the specifics of Lee's case, the broader research on extracellular matrix was continuing and showing promising results in other applications. And that's where the story gets really interesting. Part 4, the science moves forward. While the debates about Lee Spievak's specific case continued, Dr. Stephen Badylak and other researchers were moving forward with more controlled studies of extracellular matrix applications. And what they've discovered suggests that whether or not Lee's case was a genuine regeneration miracle, extracellular matrix really does have remarkable properties that could revolutionize medicine. Let me share some of the research that's been conducted since 2008. The US military followed through on their plans to test ECM on injured soldiers. Studies were conducted at the Army Institute of Surgical Research on service members who had lost portions of fingers in combat. The results were mixed but showed some promise. Some soldiers experienced enhanced healing and regained more functionality than expected. Others saw minimal benefit. The variability suggested that ECM works better in some situations than others, though researchers still don't fully understand what determines success versus failure. Meanwhile, Dr. Badylak's team at the University of Pittsburgh continued exploring other applications. One of the most dramatic involved using ECM scaffolds to regenerate portions of the esophagus in cancer patients. When someone has esophageal cancer, surgeons sometimes need to remove part of the esophagus. This is devastating because it severely impacts the patient's ability to eat and dramatically reduces quality of life and survival rates. But Dr. Badylak's team developed a technique where they would place an ECM scaffold in the area where the esophageal tissue had been removed. The scaffold would then attract stem cells from the patient's own body. These stem cells would gradually regenerate new esophageal tissue around the scaffold. The scaffold itself would dissolve over time, leaving behind functional, regenerated esophagus. The early results from these trials were promising. Patients who received the ECM scaffolds had better outcomes than those who underwent conventional reconstruction techniques. The regenerated tissue functioned more like natural esophagus. Patients could swallow more normally. Their quality of life improved significantly. Similar approaches have been tested for other tissues. Researchers have used ECM scaffolds to help regenerate portions of bladders, sections of blood vessels, patches of damaged heart tissue after heart attacks, and even parts of damaged livers. In Germany, researchers developed a technique using ECM combined with a patient's own cells to treat severe burns. They spray the patient's stem cells onto the burn wound along with ECM material, and the combination promotes regeneration of skin that's more like normal skin than scar tissue. The regenerated skin has better appearance, better function, and even includes structures like sweat glands and hair follicles that typically don't form in scar tissue. But perhaps the most exciting development has been in understanding how ECM actually works at the cellular and molecular level. It turns out that extracellular matrix is not just a passive scaffold. It's bioactive. It contains hundreds of different signaling molecules that communicate with cells. These signals tell stem cells to migrate to the wound site. They instruct cells to differentiate into specific tissue types. They prevent the inflammatory response that typically leads to scar formation. And they create an environment that favors regeneration over simple repair. One of the key discoveries is that ECM contains molecules called cytokines and growth factors that are essential for coordinating the regeneration process. When the ECM is applied to a wound, these molecules are gradually released, creating a chemical signal that attracts the body's own stem cells and guides their behavior. ECM also appears to modulate the immune system's response to injury. Normally, when you're injured, your immune system floods the area with inflammatory cells that clean up debris and fight infection. But prolonged inflammation leads to fibrosis, the formation of scar tissue. ECM seems to shift the immune response from a pro-inflammatory state to a pro-regenerative state. It recruits special immune cells called M2 macrophages that promote healing and tissue remodeling rather than just fighting infection. Another crucial finding is that the three-dimensional structure of the ECM matters. It's not just about the chemicals it contains. The physical scaffold provides a template that guides how cells organize themselves. Cells follow the structure of the ECM, using it as a guide to rebuild tissue architecture. Think of it like this: if you were trying to rebuild a complex building, having just the materials wouldn't be enough. You'd also need blueprints and a framework to guide construction. ECM provides both the materials and the framework for rebuilding tissue. This understanding has led to increasingly sophisticated ECM products. Researchers are now developing ECM scaffolds that are precisely shaped for specific applications. For example, they're creating tube-shaped ECM scaffolds for regenerating blood vessels, or sheet-shaped scaffolds for rebuilding skin, or complex three-dimensional scaffolds for regenerating more intricate structures. Some researchers are even combining ECM with stem cells that have been cultured in the laboratory. They seed the ECM scaffold with stem cells before implanting it, giving the regeneration process a head start. Early results from these combination approaches are even more impressive than using ECM alone. But there are still significant limitations and unanswered questions. The biggest limitation is that ECM-based regeneration works best for relatively simple tissues and structures. Skin, bladder lining, blood vessel walls, esophageal tissue, these are tissues with relatively straightforward architecture. They're made of a few cell types organized in relatively simple patterns. Complex organs like the heart, liver, or kidneys are far more challenging. These organs have intricate three-dimensional structures with multiple specialized cell types arranged in precise patterns. While ECM can help regenerate portions of these organs, we're still far from being able to regenerate an entire complex organ. And bones remain particularly tricky. Lee Spievak's finger apparently regenerated, including the bone, but most ECM studies have shown limited bone regeneration. Bone has unique structural and mineral properties that make it especially difficult to regenerate using current ECM approaches. The dream of regenerating entire limbs, arms, legs, hands, feet, remains distant. Dr. Badilak himself, while optimistic about the future, acknowledges that limb regeneration would require coordinating the regeneration of bone, muscle, nerves, blood vessels, skin, and connective tissue all at once, with all these tissues organized in the correct three-dimensional structure. That's an enormously complex challenge that current ECM technology isn't ready to solve. But researchers are working on it. There are labs around the world exploring different aspects of this problem. Some are focusing on improving ECM scaffolds to better promote bone regeneration. Others are working on ways to regenerate nerves more effectively. Still others are researching how to coordinate the regeneration of multiple tissue types simultaneously. And progress is being made, step by step. Part 5. What this means for medicine. Let's step back and look at the bigger picture. Whether Lee Spievak's finger regeneration was enhanced by the pig bladder powder or would have happened naturally, the case brought enormous attention to the field of regenerative medicine. And that attention has helped drive research forward. The fundamental insight that's emerging from all this research is profound. The human body has far more regenerative capacity than we've traditionally believed. We've spent centuries thinking of human tissue regeneration as minimal and limited. Wounds close, but they scar. Organs don't regrow, lost limbs stay lost. But the truth is more nuanced. Humans can regenerate, under the right conditions. Children can regrow fingertips. Livers can regenerate substantial portions of themselves. Bones can heal completely. The problem isn't that human bodies can't regenerate. The problem is that as we age, and as injuries become more severe, the regenerative process often gets hijacked by scar formation instead. ECM research has revealed that the body has a choice at the moment of injury. It can regenerate or it can scar. And which path it takes depends on the signals it receives from the local environment. If the signals favor inflammation and rapid wound closure, you get scars. If the signals favor stem cell recruitment and organized tissue rebuilding, you get regeneration. This is revolutionary because it suggests that by manipulating those signals, by providing the right chemical and structural environment, we might be able to tip the balance in favor of regeneration far more often than currently happens. This has implications that extend far beyond regenerating fingers. Imagine if heart attack patients could regenerate damaged heart muscle instead of forming scar tissue that weakens the heart. Imagine if burn victims could regenerate normal skin instead of extensive scarring. Imagine if spinal cord injury patients could regenerate nerve connections instead of permanent paralysis. Imagine if people with degenerative diseases could regenerate healthy tissue to replace what's being destroyed by disease. These aren't fantasies anymore. They're active areas of research with some early successes and enormous potential. The field of regenerative medicine is converging from multiple directions. You have ECM research showing that biological scaffolds can promote regeneration. You have stem cell research revealing how to guide cells to differentiate into specific tissue types. You have tissue engineering creating three-dimensional structures that mimic natural organs. You have gene therapy learning how to activate regenerative pathways that are normally dormant in adult humans. As these different approaches come together, the potential for genuine regenerative therapies is growing rapidly. And there's another layer to this story that's worth considering: the role of belief and intention in healing. Lee Spievak believed the powder would work because his brother, whom he trusted, told him it would work. He applied it faithfully. He expected to see results. And he did see results. Now, skeptics would say this is just placebo effect or confirmation bias. But what if belief and expectation actually do play a role in regeneration? What if the mind-body connection is stronger than we've acknowledged? There's emerging research suggesting that psychological factors can influence physical healing. Stress slows wound healing. Depression suppresses immune function. Conversely, optimism and positive expectations are associated with better surgical outcomes and faster recovery from illness. Could Lee's belief that the powder would work have influenced his body's response? Could his positive expectation have tipped the balance toward regeneration rather than scarring? We don't have clear answers. But it's worth noting that in many traditional healing systems around the world, the healer's role isn't just to apply medicine. It's also to instill hope and confidence that healing is possible. Maybe there's wisdom in that approach that modern medicine has overlooked. Regardless of the mechanisms at play, one thing is certain: Lee Spievak's story has inspired countless people to believe that healing beyond what's considered normal might be possible. And belief, even if it doesn't directly cause miracles, can motivate people to seek treatments, to stay positive through recovery, to not give up hope. So what do we make of Lee Spievak and his regenerated finger? Is it proof that extracellular matrix can trigger miraculous regeneration in humans? Or is it an example of natural healing that was documented and promoted in a way that made it seem more extraordinary than it actually was? The honest answer is, we don't know with certainty. What we do know is that Lee Spievak's finger healed remarkably well. We know that Dr. Stephen Badylak's research on extracellular matrix has opened up legitimate and promising avenues in regenerative medicine. We know that thousands of patients have benefited from ECM-based treatments for various conditions. We know that the human body's capacity for regeneration is greater than we previously believed. We know that under the right conditions, with the right signals and scaffolds, human tissues can rebuild themselves in impressive ways. Whether the pixie dust was truly magical or simply helpful or perhaps unnecessary in Lee's specific case, the broader story remains hopeful. We are learning how to tip the scales toward regeneration. We are developing tools and techniques that harness the body's innate healing capacity. Lee Spievak is still alive and well as far as public records indicate. His finger remains functional. He returned to his work at the hobby shop, though presumably he's more careful around spinning propellers now. His brother Alan continues to work in regenerative medicine. Dr. Badylak continues his research at the University of Pittsburgh. And around the world, researchers are pushing forward, trying to unlock the full potential of human regeneration. Trying to help soldiers regrow lost tissue. Trying to help burn victims heal without scarring. Trying to help heart attack patients regenerate damaged muscle. Trying to help all of us age with less degradation and more resilience. The dream of regenerative medicine is becoming reality, piece by piece, study by study, patient by patient. And whether you believe Lee Spievak's story is a miracle or a medical misunderstanding, this much is true: he got his finger back. And that alone is worth marveling at. Thanks for listening, and until next time, stay curious.